For decades, computer scientists have pursued a singular objective: building machines capable of mimicking human cognitive functions and problem-solving. We call this broad category artificial intelligence. Machine learning is a specific, narrower subset of that pursuit. Instead of relying on explicit human-written rules, machine learning uses optimization and pattern recognition to make highly accurate predictions. This diagram illustrates the precise boundaries. The outer circle represents AI, and the inner circle is machine learning. Deep learning is defined strictly by the depth of its architecture. To qualify, a model must utilize a neural network with more than 3 layers. In traditional software architecture, human engineers input data and strict operational rules into a computer to output answers. In machine learning architecture, that process is inverted. The system takes in raw data and the correct answers, and it calculates what the hidden rules must be. To understand modern artificial intelligence, we have to look past the broad industry terminology. We need to trace this exact mechanical loop: how a model ingests data, measures its own error, and mathematically adjusts itself to discover those rules. The training loop begins with data input, but models do not process raw, abstract concepts. They process isolated mathematical variables called features. These inputs generally fall into 2 categories. Continuous features contain floating point ranges with infinite possibilities, like a temperature reading. Discrete or categorical features are limited to specific, finite sets, like the red, yellow, and green states of a traffic light. This visual demonstrates a data preparation technique called bucketing. Instead of feeding the model an infinite continuous temperature scale, the data is chopped into distinct blocks: cold, temperate, and warm. This simplifies the information, allowing the model to treat all values within a specific range identically. Looking at this diagram of a single neural network node, we see how the data enters the actual architecture. The node receives these incoming feature values, multiplies each one by an assigned numerical weight, and calculates a total weighted sum. Next, the node adds a bias term. This acts as an intercept, shifting the mathematical logic off the 0 origin point. Without a bias term, a model's calculations would always be anchored to 0, severely limiting the patterns it could identify. The final step inside the node is the activation function. The node passes the result of its weighted sum and bias through a specific mathematical curve, like a sigmoid or ReLU function. This function maps the weighted sum to a nonlinear output. Without this nonlinear transformation during the forward pass, a neural network could only ever model simple straight lines. It would fail entirely at capturing the complex variables of the real world, regardless of how many layers it contained. Once the data completes the forward pass and generates a prediction, the network has to evaluate its own work. This initiates the backward pass. The system calculates loss, the exact mathematical difference between the network's prediction and the actual verified ground truth label. To reduce this loss, the network relies on an algorithmic engine known as backpropagation. As this network diagram illustrates, backpropagation moves in reverse. It travels from the output layer back through the hidden layers toward the input. Using the chain rule from calculus, the system calculates the partial derivatives of the error and precisely adjusts the weights applied to particular neurons to minimize the loss. This calculation isn't done on the entire dataset at once. The network processes a specific subset of data examples, called a batch, during a single forward and backward iteration. Once the system has processed every example in the entire training dataset one time, it has completed a single epoch. A machine learning model is grown through thousands of these epoch cycles. With every single iteration, the backpropagation process incrementally carves away the mathematical error until a reliable predictive engine remains. If a model learns by continually looping through the data, how does an engineer know when to halt the process? The objective is a state called convergence. This occurs when the loss values change very little or not at all with each new iteration. This graph visualizes convergence. The line tracks training loss over time. It drops rapidly as the model corrects its largest errors, and then flattens out as additional training iterations stop yielding significant improvements. Letting a model train indefinitely creates a specific danger called overfitting. The model stops learning general patterns and begins memorizing the exact training data. rendering it useless for processing new, unseen information. To prevent overfitting, engineers utilize a regularization technique known as early stopping. We can see early stopping in action by adding a second line to our graph, representing the loss on a separate validation dataset. The system tracks this validation loss during training, and the moment that line hooks upward, the timeline halts. Successful machine learning engineering requires strict boundary control. You have to terminate the training loop at the exact mathematical moment before the model loses its ability to generalize to new data. Building a converged model is only the first phase. The architecture must be rigorously stress-tested to prove its predictive limits in the real world. The most common metric for this is standard accuracy, the number of correct predictions divided by the total number of predictions made. But accuracy is highly misleading when applied to a class-imbalanced dataset. Consider a climate scenario where it only snows 25 days out of an entire century, a span of 36,500 days. Look at the data table for a broken model that hard-codes a no-snow prediction every day. It correctly identifies 36,499 days, achieving a 99.93% accuracy score. Despite this, the model has zero predictive power, failing completely. Evaluating ML models on class-imbalanced datasets with flat accuracy metrics creates a dangerous illusion of success. It rewards models for exploiting the mathematical imbalance rather than recognizing actual patterns. To solve for this illusion, engineers rely on multidimensional evaluation, starting with the confusion matrix. This 2x2 grid categorizes predictions into 4 distinct quadrants: true positives, true negatives, false positives, and false negatives. Rather than providing a single volume of total errors, the matrix reveals exactly what specific types of mistakes the classifier is making. But there is still a human variable. A logistic regression model outputs a raw probability, say 0.85. An engineer sets a classification threshold that dictates whether that 0.85 counts as a positive or negative prediction. Manually shifting this threshold artificially alters the false positive and false negative rates within the confusion matrix, further complicating standard evaluation. To prove effectiveness regardless of where a human sets that threshold, we measure the area under the ROC curve, or AUC. This graph plots the ROC curve by measuring the true positive rate against the false positive rate across all possible thresholds. The total shaded area beneath that curve determines the AUC. An area filling up towards a score of 1.0 represents perfect class separation, while a score of 0.5 indicates a model that is no better than random guessing. AUC-ROC proves a model's foundational predictive effectiveness mathematically, entirely independent of the operational parameters set by a human engineer. Mastering the mathematical architecture of a neural network is only half the equation. The outputs of these models are ultimately bound by the raw data they ingest at the very beginning. There is a sharp distinction between a mathematical bias term, which correctly offsets a function during the forward pass, and an ethical bias, like a skewed sample or implicit prejudice, which silently corrupts the training data. A model is exactly as neutral as its inputs. Developing responsible, highly accurate artificial intelligence requires optimizing both the mathematical precision of the architecture and the integrity of the data it learns from.